So I'm going to continue my lectures, still focusing on the information paradox. I will start with a quick review of what we talked about last time, and then take some questions. So last time we were talking about this solution that we wanted to study of this eternal black hole in ADS. So this is a solution of JT gravity. It's a two-dimensional theory of gravity. Inside this rectangle here, we have the eternal black hole in ADS2. And for some strange reason, which will become clear later, I decided to include these flat space asymptotic regions, which I call baths, on the two sides. And I've made the assumption that along the boundary of ADS2, we have transparent boundary conditions on the matter. For gravity, we have Dirichlet conditions, the usual Dirichlet conditions here of just having asymptotically ADS2, but the matter can go through into the flat space regions. The metric of the ADS2 spacetime can be written in various coordinate systems. One coordinate system is the usual Poincare coordinates, expressed in light cone coordinates, or light cone gauge. One can equivalently use a different coordinate system, this y plus minus, which cover just the regions outside of the black hole or the wormhole. And those coordinates, those black hole exterior coordinates, extend naturally to the coordinates on the flat space side. Okay? All right. This system here, you should have in the back of your mind that it has a dual description in terms of, let's say if ADS2 is dual to SYK, in terms of two SYK dots, L and R, coupled to two flat space half lines going all the way to infinity here. Okay? Question? Yeah.
Do you have an idea of how to write this explicitly in the terms of SYK?
I do not.
Well, what do you mean going up to infinity? There's no space. Just like on your calculator.
Sorry. BR here,
Yeah.
a space-like slice of the bath system is just a half line. That's what I mean. So usually consider field theory on the real line. Okay, but now I'm just kind of cutting it in half.
No, I understand field theory of the real line.
Okay.
That's what this quantum wire is. It's just a free field theory half line.
Oh yes, here we have a free. Oh no. I'm considering a general conformal field theory. General two-dimensional conformal field theory that lives on this half line.
Yeah.
Hold on.
I was just asking in the dual.
In the dual, technically speaking, in what I'm talking about here, you should really think of it as the same CFD here. Okay? But in terms of, but in that case, this R I don't think should be thought of as SYK. Okay? I don't know what it's going to be. But had you started with SYK here, I don't know what the natural thing you should consider here to couple it to SYK.
Wow, gravity is also one higher dimension.
No. So the bath is 1 plus 1 dimensional. So is the ADS2 region. Here I'm only showing space. Okay.
This 1 by epsilon square dy plus it's throughout the space?
Yeah, this is the metric throughout the space.
Black metric?
Yes, because it matches onto this metric along the location epsilon. Okay. Something else we talked about last time is what happens when you do coordinate transformations and Weyl transformations, what happens to the stress tensor. I should emphasize that this is what people mean when they say conformal. Is there a question? Conformal transformation. So conformal transformation in CFT, it's a combination of a coordinate transformation and a Weyl transformation. For instance, it's something like this, going from, let's say, some y coordinate to some w coordinate, where w is now a function of y, and I'm assuming this is a holomorphic transformation, so w plus is only a function of y plus, something like that. And when you do this transformation, the relation between the stress tensor defined on the flat w metric is related to the stress tensor on the flat y metric by this relation. Okay? So there's this tensor transformation factor plus this anomaly term, the Schwarzian derivative. Okay, the black hole solution is a vacuum solution of JT gravity, which means that the expectation value of the stress tensor is 0. But one has to be careful when you make such statements. It's 0 with the ADS2 metric. You can choose to express, well, you can do a Weyl transformation, and you can remove the ADS2 factor, and it would give you that the stress tensor on flat space is given by this. Okay? Now, what we mean by transparent boundary conditions is that this is also the value of the stress tensor in the bath. Okay?
The interval between the bath and the ADS2, is it like a domain one? I mean, is it really static, or by changing the temperature of the bath, it will move from one side to the other? Or how do you do it?
So the location of the boundary is given by this epsilon. Okay, so you can, for example, you can.
And it's fixed if you increase the temperature of the bath. It will
No, this epsilon is this epsilon is just fixed. It doesn't depend on beta on the temperature, and ultimately it's just a regulator which we're going to take to 0 at the end. Okay, any questions about the stress tensor? Okay, then we talked about, very briefly at the end, well, I introduced the topic of black hole thermodynamics. So suppose we are interested in the partition function as given by trace e to the minus beta tilde h. Beta tilde is just it's the inverse temperature that I'm specifying of my canonical ensemble. The proposal of Gibbons and Hawking that we can compute the partition function of gravity, or of the eternal black hole specifically, by by evaluating the gravitational path integral on the Euclidean black hole solution. By that I mean you just evaluate the partition function or the path integral on the saddle point given by the Euclidean black hole solution. And here I'm just saying that this is a saddle point of the path integral subject to having periodic boundary conditions at infinity with or rather that you have a time circle at infinity whose length is beta tilde. The reason why it's at infinity is because the Hamiltonian of the theory is a boundary term. It's gravity, so the Hamiltonian is at infinity. So on the saddle point, we just have something like this. I'm ignoring matter. I'm just focusing on gravity. And it's the classical action evaluated on the saddle point. Well, it's the same thing. And we also talked about what is a Euclidean black hole. The Euclidean black hole is what you get by starting with the Lorentzian black hole, this metric here, and you continue the time variable, the time here being the black hole exterior time, that is something like this, which is also this. It's the same time that's on the bath side, and you continue it to some Euclidean time variable. Okay. So now we have the partition function. We can extract many properties of the black hole from it. One important property is the thermal entropy. That's given by this formula, 1 minus beta tilde d beta tilde of log z, which means we can just put in the on-shell action here. And here I'm specifying that I'm doing this for the theory that we're analyzing, which is JT gravity, evaluated on the eternal black hole. Okay. Here's a picture of the Euclidean black hole. It's what you get by slicing this spacetime in half over here and continuing to Euclidean time. This is the famous cigar geometry. Here it's written as it's just flattened out as a disk. The cigar goes all the way to infinity. This point really is at infinity, or rather this circle here is at infinity, but it's just because here I did a conformal transformation, brought infinity to a finite place. Tau, this Euclidean time variable, has periodicity beta tilde. Here is what the dilaton looks like. The dilaton also has symmetry along it's constant along the time direction, and it grows as you go it grows as you go towards the boundary. And so one thing I want to emphasize is if you look at this this metric here, at least the continuation in Euclidean space, and you focus on it near the tip, you find that the metric looks something like this, where r is some radial coordinate measured away from the tip, plus r squared times the combination 2 pi tau over beta tilde squared, which if you define as a new time variable tau hat, the fact that well, what you find is that tau tilde has periodicity 2 pi, which is what you need in order to have a smooth point here at the origin. I'm going to start playing around with that in a second. Any questions about that? I'll give you guys a sec. I'm going to start erasing.
Can I ask a question about the boundary conditions?
Okay.
So how, I mean, if it was not a flat space, but some other non-zero curvature space that you were trying to do,
I can say I can combine this to another ADS2, for example.
Okay, and if there was can you have reflecting boundary conditions if you have a singularity there? Because I saw a paper that they were saying that even with a singularity they have that.
Sorry, you mean that there was a singularity here?
Yeah.
Even in this case, there's a delta function curvature singularity. Yes, curvature singularity.
So even across the singularity.
Well, the nice thing is that in this theory, this theory is so stupid, the matter can just propagate through that singularity, and it doesn't feel it.
In the 2 dimensions.
Yes, in the 2-dimensional case.
But in 4 dimensions.
Yeah. Well, you can regulate this actually. Like here, I was imagining that the metric is only continuous. Okay, but you can try to find some C infinity way of going through the ADS2 region to the flat region, which would remove that singularity. But it might insert some localized energy source there. But you can make it as mild as you want, I think. Any other questions? Okay, so let's yes. Okay. Let me do the following thing. So let me write this as the limit of beta tilde going to so rather beta going to beta tilde, where beta is greater than beta tilde, of this object, 1 minus beta d beta by jt. I'm going to write this way, g beta. Okay. So far I didn't do anything. Yes?
Can you just remind where beta is the parameter in the where does beta enter? Not beta tilde, but beta?
It only entered here.
Why?
So far I just relabeled beta tilde to beta, and I'm taking limit as beta goes to beta tilde.
So on this side of the board we have no beta, just beta tilde?
Correct. This is the first appearance of beta in this talk, in today's talk. Okay. Okay. Now I'm going to start playing around with this. Now let's say that you have beta. Let's focus on, let's consider this solution. This solution is what I'm drawing here. Beta tilde is less than beta, so there's so beta tilde is like this length here, okay, and the length all the way around is beta. Okay, you can imagine doing a quotient where you take tau to tau times beta over beta tilde, and you'd get the same space-time, but where you have a conical singularity here. Okay? And in this picture, tau goes as tau plus beta tilde. So here we have a conical singularity of deficit 2 pi beta tilde over beta. Or rather 1 minus that. Let me see. Having this singularity here, it means that, so if I give you the space-time, and if you compute, say, 1 over 16 pi g phi times r, what you will get is phi evaluated at the conical singularity over 4 g Newton times 1 minus beta over beta tilde. Well, this makes sense. If I take beta to go to beta tilde, then I'll get 0. Why is this? Why am I doing this? If you go back and look at the action of JT gravity, and you evaluate it on the eternal black hole solution of solution with inverse temperature beta, you can. I don't know how explicit I should be. You can write this as beta over beta tilde times the same JT action, but evaluated on the singular space-time. Because we evaluated this on the singular space-time, it picks up this extra contribution. The integral phi r has that piece, which means we have to subtract it. Subtracting it means you add this term. you need to add this term to get rid of the contribution of the conical singularity when you do this. Okay?
Why do you think that the action is just a function of the network and also the
it is also a function of the dilaton. I'm just focusing on the metric. Yes? Yeah.
The formula, I don't see why there is the dependence on x there.
X. X here means this point.
Oh, I see.
Yeah, sorry. So I don't know what. 0 is a good one. Yeah. Good. Okay. Okay. So the point is that so the JT action has an integral phi r term. That's going to pick up a contribution from the singularity, the conical singularity, which has to be subtracted out.
So why is that phi 0 plus pi horizon?
Horizon means 0. So this entire thing here is what I meant there at 0. Remember in the JT action, there was a phi 0 r term, and there was a phi r term as well. It was more like this. This thing plus k, and there was this thing plus 2 plus phi bk. And what I'm saying is that this term plus that term on the singular geometry gives us this piece. Okay. But now notice that all of the dependence on beta is out here. So when I take this derivative, or I act as a differential operator, it just acts on these betas. It's going to kill this term. So this term is just gone. And it's going to remove this factor. And so ultimately what we get is that S thermal is just equal to phi naught plus phi at 0, which is really the horizon, or more carefully, it's the bifurcate horizon. Divided by 4 G Newton. Okay?
Start notation.
Yeah.
Phi parenthesis 0 here is phi evaluate at the horizon.
Good.
And then there's, well, you also said the sum is also phi parenthesis 0.
sorry. I said, what I meant was, this is what here, I'm just, you should think of this as phi, well, let me say it again. In the JT action, we have something that looks like this. Okay? That was a general discussion. Okay? We have something like this. So some function of I times r. Because of the conical singularity, we are going to get a term that looks like this. Just to stick with to notation, it's going to be this thing at 0 and this thing at 0. But phi naught is constant, so it has no argument. But phi depends on the space-time point. And by 0 here, this 0 here is really the center over here, which in the Lorentzian geometry corresponds to the bifurcate horizon.
Sorry, there's something very basic I don't understand. G Newton I used to see as the coefficient of square root of minus GR. Here is integral phi r, and then we decided to call some coefficient G Newton, but why should I think about it as G Newton?
It's the coupling constant of gravity. So you put in the action of JT gravity, it's 1 over 16 pi g. So what you're saying is that usually we do this, right? Yes. But in this theory, it's a dilaton gravity theory. So it's r times phi. Oh, is there a question about what?
Some value of phi will determine G Newton.
Oh, sure. Let me absorb 1 over 16 pi g into phi. If you
Then I
do,
understand.
yeah, if you do that, then you get this. Okay. Yeah, no, you're right, you're right. Okay. All right, so what is this saying? So this is the thermal entropy as computed from some canonical partition function. Had you done this calculation with your eyes closed, then you would have said that this is, well, first it would be very impressive. Second, this is the log omega, where this is the number of microstates it's usual thermodynamics. It's the number of microstates given some macro state. Here, the macro state is described by, I guess, the temperature, or the mass. Yeah, the mass. The mass is. That's right. And this tells you that you have exponential of this many degrees of freedom. This is not sorcery. I don't know what is. We were trying to compute a trace of something. And we only looked at one gravitational solution. Might have expected to get 1 or something. Or just log, well, 0, because it's just one microstate. But you get a very large number. So somehow gravity is telling us that this black hole, well, it's hinting at this, that black holes can have many different microstates. Okay. Yes.
Why do you refer it to as a solution rather than an Onshell configuration?
Because it's a solution. It's an Onshell configuration.
But the Conical Singularity being put into function are not satisfied.
Correct, but I took beta to beta tilde. So here I used a trick of going slightly off shell and then coming back, but I didn't have to do that. Okay.
But so in what sense is this a large number? I mean, so phi naught is much larger than g.
Yeah. So the assumption here is, in order to have perturbative gravity, in order for the coupling constant of gravity to be small, you need the coupling constant here is really g Newton divided by the phi's. Let's take phi naught to be very large. Then yeah, the coupling constant is g Newton divided by phi naught. And we want this number to be very small, and hence S is very large. And yeah, that's okay. All right. The next thing is going to be computing the quantum state of the Hawking radiation. Well, I guess first showing that there's radiation and then computing its quantum state. Question? Yes?
So you're looking that the angle is 2 pi beta tilde over beta, and then but also when you compute it, you took beta to be beta tilde. So if there's no it, there's really no conical singularity?
At the end, there's no conical singularity. Yes. Okay. Let's see. Give me a sec. So my iPad is freezing. Okay. All right. Okay. So.
Why did you have to go in such a way to the entropy? If you're only interested in the entropy, add the circuit to space, and the area of the horizon with the size of the circuit, and size of the G Newton.
But how do you? But how do you know that that computes the entropy?
It's the area of the horizon.
I'm deriving the fact that the area of the horizon is the entropy.
Ah, you want to derive it. Okay.
Yes.
No, I understand.
Yeah.
No, I keep on talking short.
Yeah.
It's equivalent.
Well, yeah, I can just dictate,
No, I understand the logic.
Okay. All right. So what I'm going to do now is to compute the quantum state of the matter. Okay, so quantum state of matter, and we're going to do that via sort of conformal anomaly tricks on the entire system. So, okay, so we had a picture like this. Where we had the y, so the y plus minus coordinates, they covered this region or this region. Okay? So you should think of there being two y plus minus coordinates. There's a y plus minus r and a y plus minus left. Okay? You can do, and the stress tensor is not equal to 0 in the y coordinate system for any plus plus or minus minus, assuming you have a flat background. Okay, so this is not equal to 0. Something you can do is that you can find a new coordinate w of y, also holomorphic using these tricks, where w covers the entire space-time. By that I mean it covers both Bath regions. Both Bath regions, yes. So this diamond here is this diamond. Okay? And the transformation is, roughly speaking, it's exponential. So w goes as e to the y over beta. Something like this. There are a bunch of plus minus signs depending on whether you're looking at plus or minus. On this, so here w plus minus covers the entire diamond. Diamond, or let me just say space-time, all the space-time.
But you're mapping both the left and the right?
Yes. Yes. Mapping both the left and the right to the whole thing. And that's going to be important. Let me erase that. Sky plus here corresponds to w plus being infinity. Sky plus here corresponds to w minus being infinity. W sky minus here is minus infinity. And this is w minus equals minus infinity. Okay? The advantage here is that the stress tensor in the w coordinates is equal to 0 on flat space. Okay? What this means is that in the w coordinate system, the quantum state is simply the vacuum. Okay? So I'm going to say it this way. I'm going to say that the state in the w frame is the vacuum. That simply follows because the expectation value of the stress tensor is 0. We can, okay. Let's talk about various ways of defining time evolution. One way in the w coordinate system corresponds to just regular Minkowski time. going like this, going up. In the y-coordinate system, we had a time here and a time here. It's natural to consider, well, okay, you don't have to. So here's time on this side. And on this side, we have also time does something like this. Okay. Okay. If we consider the time evolution generated by, so here this is the time evolution generated by, let's call it HW. Here, the time evolution here, let's say it's generated by H left. Time evolution here generated by H right. If we consider no, actually that's not important. Okay, so HH, that's good. The goal is to express the vacuum state in the W in the W frame in terms of some superposition of states of the left and right Y frames. The way to do that is just something like this. So now I'm just doing a basis transformation. Yeah.
About this statement is about the expectation value of the energy of momentum tensor in the W coordinate. Can you explain what you mean by that? Is it just in the ABS region? Or
no, everywhere.
Everything is flat?
Everywhere. So
does it not mean the W needs to be an SO2Z transformation of, so it is?
It is. Ah. Yes, it is. It is an SL2C transformation of the X coordinate, the Poincare X coordinate.
But if we said that the expectation value vanished of the energy momentum tensor vanished in the W, in the Y coordinate?
Yeah. So okay. Okay. So in the TXX in AES2, okay, that was 0. We can compute the TXX on flat, and it's actually also 0. Okay, X is different from Y. The conformal factor, and rather the Poincare conformal factor, actually gets killed by the Schwarzian derivative. Okay, so TXX is 0, and then the relation between X and W is an SL2 transformation.
So, and this is true just for flat and ABS, or any metric, if I write X in any kind of metric, it's always going to be 0?
Any conformal transformation defined by conformal means something like this, where it's an SL2 transformation that's going to preserve the value of the, well, by preserve I mean this anomaly term is going to be 0. Yeah. Okay, so we want to compute the quantum state, the Y frame. So we want to compute basically these coefficients. The way to do this is to first note that the vacuum state in W is prepared by the following path integral. It's basically it's just a matter path integral starting from minus infinity in Euclidean time and evolving up to some time t equals 0.
So here we cover
our left-right energy eigenstates of this Hamiltonian. That's what I was going to say here. So this would mean that if you want to compute something like this, what you have to do is project this side here on with the energy eigenstate E tilde of the H of HR, and over here project with the energy eigenstate E. Because these H's generate this time evolution in Lorentzian time, when you continue that Lorentzian time to Euclidean time, it corresponds to this evolution, which means that that Hamiltonian also evolves you in this direction in Euclidean time. But if that's the case, this means that this diagram that I'm drawing here should be thought of as the overlap e to the minus beta over 2h times e tilde. And h here, it's hl or hr, it doesn't really matter, which is a delta function, e tilde, e to the minus beta over 2e. This means that the vacuum state in the W frame can be expressed as the following in the left and right Y frames. So the vacuum state in the W frame is some entangled state of the fields on the right and the left. For the case of this is general for any kind of matter theory that you want to consider. But if you focus on a free theory, so this is going to be some product. This is a product over frequencies, sum over occupation numbers of e to the minus beta n omega over 2. I'm being schematic. Okay. What this says is that, so each of these eigenstates, and so let me emphasize, this is free case. In this case, these eigenstates m correspond to plane wave solutions on either side. Okay? Right. And they're entangled. The picture I want you to have sort of in your mind is that there's just a bunch of particles that are entangled with each other. And the entanglement is in the occupation basis. 0, 0, 1, 1, 2, 2, 3, 3, and so on and so forth. And there are many modes. You know, there are right-moving modes. There are also left-moving modes, and so on. Okay? Notice that the right-moving modes are entangled across this horizon, and the right-moving modes are entangled across this horizon. Okay. Any questions about that?
What do you mean that they're entangled along the
I just mean that what do I mean? In the next step, I'm going to compute entanglement entropy, and maybe it's going to be clearer there.
This is just a purification of the thermal state.
Correct. This is the purification of the thermal state, or the thermal density matrix of any of the two sides. Right? If you take this and you trace over, let's say, the left, then you get a density matrix for the right, which is just e to the minus beta h. You get the canonical density matrix, the canonical density matrix.
Ahmed?
Yes?
Just one question. E is for the left path and E tilde is for the right path.
Yes, yes.
But if they can involve to each other, so
If they can what, sorry?
if they can involve to each other, so they are in the same Hilbert space, the left and the right.
Here?
How do you do a tensor product of that?
So they're not the same Hilbert space, but here we have the thing about Euclidean field theory is you can change which way you can choose which way to evolve states. Okay? So you can think of this as either I'm preparing a state on this slice, which is some is some state on the product Hilbert space. Or you can think of it as an evolution from this half to that half. I'm saying that this other way of thinking about it buys you something. It tells you that this E and E tilde have to be the same if you're projecting. Okay? Any other questions?
You said in the beginning that you make a general conformal fitting.
Yes, yes.
Now you make it free.
This is just for this is just an example to build some intuition, but I'm not going to use this. Okay. Okay. Next, I will talk about the techniques for computing von Neumann entropy. Did Zohar talk about that?
Replica was not.
No, but he talked about entanglement entropy.
He mentioned it like 5 minutes.
Did he say that it's given by the 2-point function of twist fields? Okay. Thank you, Zohar. Okay. Okay. Let's see. All right. Okay. Okay. So, entanglement entropy. Or just entanglement entropy. So, the formula for entropy is, so okay. We want a measure, so I claim that there's entanglement between the left and the right. And we want some precise formula that measures that entanglement. Yes?
Yes. Question with
yes.
So the statement the voluminous, you didn't care about symmetric discontinuity?
Remember, thank you. So I did this entire thing, I derived this state after I removed the ADS2 factor. The ADS2, I Weil transformed away the ADS2. It's in flat space. Now you can put back in the ADS2 Weil factor, and I claim it's not going to change the state. It might change it slightly, but it's not going to change the.
It's an eigenstate
let me see. But I think there's a one-to-one mapping between the eigenstates of the first Hamiltonian and the eigenstates of the Weil transformed Hamiltonian. And that's all I need. Okay. Von Neumann entropy, SVN, is given by minus trace rho log rho. Okay? There's a trick to computing this quantity, which is known as the replica trick, where you replace, well, logarithms are hard to compute or evaluate, so instead what you do is you, because I forget the precise details of the formula, so I'm trying to find it. There's one that I like and one that I don't like. Okay. I like to write it this way. This is minus partial n trace rho to the n as n goes to 1. Okay?
Over n minus 1.
No. If you're doing just, yeah, I'm taking a derivative. I don't like the other one. I like the derivative. Trace, so this is rho of some region. Let's call that region A. So in order to compute the entropy, what we need to do is evaluate trace rho to to the n of the region A. What does this mean? Let's first consider, let's say we have a state, suppose we have a state of an entire system obtained by, I'm going to write it this way. Suppose I start from, let's say here, this is minus infinity in Euclidean time. I evolve up to some time here. Okay? That prepares some state for me. So this is like the state psi. Let me consider the brawl. Let me draw it here. This is plus infinity. This is psi, brawl. If I glue this part to this part, then I'll just get 1. Okay? To compute this quantity, you first need to compute rho of A. Let's say that A is this region here. Here it is in the ket, and here it is in the brawl. Rho A is obtained by tracing out the complement of A, which means that I glue everything except for A. Actually, let's just for simplicity, let's take A to be a half line, or something like that. And then to compute rho A to the n, I need to include n copies of this all the way down, and then I need to glue them. I need to glue the first to the second. The ket of the first to the brawl of the second, and the ket of the second to the brawl of the third, and so on and so forth, all the way around in a cyclic way. This picture I can represent by the so-called orbifold picture. So I can write this as I can represent this. Sorry. This trace rho A to the n is the partition function of the theory evaluated on this manifold. Okay? This manifold I can represent by this quotient picture, okay? Where I need to go, this point here is supposed to be this point. I need to go around this point n times in order to come back to the same location. What this thing does is that it represents the computation of trace rho A to the n to be some correlation function of a defect operator that creates this conical excess. And that defect operator I'm going to call sigma n. Okay. Okay. In the case where you have a finite interval, it means you insert 2 sigma n's. Because maybe technically it's sigma n, sigma minus n in order to cancel the branch cut. Okay. It's a result from conformal field theory that these defect operators behave as conformal primaries, and this is a 2-point function of conformal primaries. So it's entirely fixed by conformal symmetry, and this is given by 1 over the distance between them. Let's say that's x to delta n, where delta n, I don't know where it is. Something like it's like c over maybe 12 n minus 1 over n. Something like that. So as n goes to 1, the dimension goes to 0. What we need. Okay. So that's how you define the entropy, and this is how you compute it.
But there's an assumption here. I mean, this is the point where you introduce some assumption about
yes.
about the behavior
Carlsons theorem, yes, yes. Let me see. What can I say about that? So what you need to do is, so in theory, you need to do this for all integer n, and then find the right analytic continuation subject to some conditions. Or rather, if you show that your expression falls off in some nice way in the complex n plane, then the analytic continuation to non-integer n is unique. And I think that I'm pretty sure that entitlement entropy satisfies those conditions, which I don't remember off the top of my head. What that means is that it's okay for us to, well, we're going to take a derivative with respect to n. Okay, so that assumes that n is just some continuous number, not necessarily an integer. Anyways, the upshot is the following.
Are you starting with some conformal field theory, or these are the discrete fields are like the safety of primary or anything?
No, conformal field theory. Yes, yes, definitely conformal field theory. What I'm saying was, so trace row to the m is computed by evaluating the partition function here. Then I'm saying that the partition function here can be represented as having a single CFT, but with an orbifold singularity.
These are operators in this.
Yeah. Okay. Anyways, the upshot is that S of row A is given by C over 3. Let's say that row A goes from x1 to x2. It's given by this nice formula. x1 minus x2 over square root epsilon 1 epsilon 2. Okay. I'll tell you what these epsilons are in a second. In null coordinates, this thing is something like this. Right here, what I'm doing x1 and epsilon 1 and epsilon 2 are UV cutoffs that you need to impose along the, well, at the interface between A and A bar. The reason why you do that is because it's a conformal theory. So you have entanglement between A and A bar at all scales. Okay? As you go, basically you have an infinite amount of entanglement across any boundary. To get a finite answer, you need to cut off which modes you want to count the entropy of. And that's epsilon 1, epsilon 2. And here I'm just writing that in terms of the null coordinates.
Question? Suppose that you take instead of general conformal field theory just free scale, then is it not possible just to calculate directly the entitlement entropy and not going over this whole release story? And then
So how are you doing it for a general theory?
What? Well, in that case, I only can diagonalize the density matrix and plug it into the expression for the entropy and get the result. No?
If you can do that, yes, but
I thought that for scalar field theory, what plus one can do.
That's a conformal theory. Sorry, scalar theory, massless or massive? think for massive, I don't think you can do it.
You claim that I have to go via this
No, you don't have to, but I don't know if you can actually diagonalize the matrix as you claim.
Suppose that I can, then it will be the same expression, but instead of C, there will be 1, and so I will
Yeah.
for any
In principle, yeah. In principle, yeah. You don't have to go through this method, but in conformal theories, this is a convenient way to do it. Because all you don't need to diagonalize anything. You just need the 2-point function of primaries. Okay.
What are these? Can you explain again about these cutoffs?
Okay. So the cutoffs is just a statement that there's an infinite amount. So I want to compute the entanglement between this region and its complement. And what I'm saying is that there's an infinite amount of entanglement between these two regions because there's entanglement at all scales. It's a conformal theory. Right? There's entanglement at all scales, and so you'll get an infinite answer, and so you need to cut it off to get a finite result. Yeah.
And that expression for a 2-point function, it could be a constant.
Yeah, there's an epsilon here. Is it the same? Yeah. What this thing actually is that it's actually it's epsilon of delta. You should think of this epsilon as it's like a renormalization of the operator. That factor is always there, even for standard operators, but we usually just absorb it. We just ignore it. Okay. Why? Okay. So now, why am I making a big fuss about these cutoffs? Is that it's actually going to be very important for the physics. Let's talk about computing entropy in that eternal black hole space-time. So let's see. Suppose we want to compute the entropy of a region like this. Okay? So the first step is to pick the endpoints. Let's call them y1 and y2. And then to pick the cutoffs, epsilon 1 and epsilon 2. The cutoffs are specified as some fixed proper distance from these 2 points. There's an epsilon. Let's say we look at the cutoff here. What we mean by the cutoff here is the following. It's some fixed number equals to the proper distance at this point. Okay? So at y1. And similarly at y2. Here we have ADS2. Here we have flat. Okay. So when I say proper distance, I mean proper distance with the physical metric in that region. The second step, well, the issue is that these formulas here that I was talking about, for example, this is given by a 2-point function, rather than this is just a 2-point function of primary fields. That's a statement about the theory on flat space, the flat metric. Here we don't have a flat metric. So what we need to do is we need to transform to the W coordinate, or map to the W frame. The W frame that we talked about earlier. So then we have just Minkowski space going from W of y1 to W of y2. Here, we know what the answer is for this entanglement entropy. is just given by this formula. Now let me just replace all these x's with w's. W, 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 W. And the cutoffs are also going to be in W. Okay? I'm just applying the formula. But these cutoffs are not the physical cutoffs. The physical cutoffs were cutoffs as measured using the physical space-time, the physical metric, not this weird metric, this auxiliary flat metric that we just put in here for sake of making simple. So we need to know how to transform, or rather, how are these cutoffs related to these cutoffs? And that's easy. Well, it's the relation between this metric and this metric. I'm putting the epsilon squared there. This epsilon is not this epsilon. This was the cutoff epsilon from before. So we need to know how are these two things related. Well, they're related by dw plus, dy plus, same thing with minus, times epsilon squared. Okay? This thing here is epsilon w plus, epsilon w minus. This thing here is epsilon y plus, epsilon y minus. So we take this answer, we plug in what w is as a function of y. So now we have in the numerator some function of y. And in the denominator, we can express these cutoffs in terms of the y cutoffs and also an additional function of y. Okay? I just noticed that, this is actually, so there's actually a missing factor. This is what happens here, because I went from this metric to this metric. This is the physical metric in the flat space region. But for here, it's not just this. I need to consider dy plus, dy minus divided by sine hyperbolic squared, so on and so forth, and also multiply here by the same thing. So then, and it's this thing that is, so this is epsilon y1, epsilon y plus y minus at location 2, and this thing is epsilon y plus epsilon y minus at location 1. Okay? So the relation between the cutoffs, between the w cutoffs and the y cutoffs depends on where you are, because the physical metric is different. Okay. Very good. Now we have the formula, so let's apply it.
I'm sorry.
Yes.
What is the purpose of doing the calculation?
Why am I talking about this? Yes, because of the following application. Let's go back to our spacetime. Ultimately, we were trying to understand this thermal entropy that we found. And we're also just reproducing Hawking's calculation. So I claimed that there's entanglement between the left side and the right side. And so what we're going to do is we're going to compute the entanglement entropy of the following region, the union of this region and this region. I'm going to think of this as the entanglement entropy of the baths, okay, of the left and right baths. You can think of this as the limit of this point going all the way to the boundary. Okay? And I'm going to study this as a function of time. Okay?
All of the things that we've done seems to introduce a time entropy in order to do this calculation.
Yes, yes.
And why do we want to do this calculation?
That will be clear in a second. Motivated. That will be clear in a second. Yes?
So the reason you draw the interval goes also to the ADS side, is it a well-defined quantity in the JSP category or not?
Yes, it is.
So how do you define
Just because it's defined in the sense that I can first remove the conformal factor, define it there, and then put the conformal factor back in.
I mean, because the metric fluctuates.
Because?
Because the metric fluctuates.
No, the metric is fixed to ADS2. Because of the when you integrate out the dilaton. We're here I'm talking about, well, more generally, even if the metric was fluctuating, I am talking about entanglement entropies of intervals on the semi-classical geometry, okay, on some saddle point. That's more generally speaking. But in this case, it's more than that.
But if you compute, in fact, the entanglement entropy of the conformal field theory in the background of this black hole solution, but it doesn't seem to include the entropy of the black hole itself.
Correct.
So, I mean, is it not that you are interested in the entropy of the black hole?
Yes, but as a first step, I'm going to compute the entropy of something else, which is going to give me information, or rather, which should give me information about the entropy of the black hole. For the following reason.
Stuff that came out of the black hole.
Exactly, it's stuff that came out of the black hole. But also, if you have a pure state of two systems, A and B, then the voluminous entropy of A is equal to the voluminous entropy of B. If you are in a pure state. If you are in a global pure state. Okay? Yes, I will argue that. Okay? Yes, okay. Well, let me argue that in multiple ways. First, given this picture here, remember we said we know what the quantum state is on a slice that goes all the way through. It's this Hartle-Hawking state. I guess I forgot to call it Hartle-Hawking, but that's the Hartle-Hawking state, the thermal field double, etc. And that's a global pure state of everything. Okay. Now we're going to compute the voluminous entropy of the outside region, the baths, from which we would have an answer for the voluminous entropy of the complement, which is the wormhole. Okay, so in this method we can assign an entropy to the wormhole, and then what we want to do is compare that to the thermal entropy. Okay. Okay. So we want to compute now the entropy as a function of time.
The thermal entropy should be identical to the entanglement entropy?
No, good. So it's a theorem that the thermal entropy is greater than or equal to the voluminous entropy from quantum mechanics. Yeah. It's something that's actually not too hard to prove. Just let me give it as homework. It's actually pretty simple. All you need to do is, it's just a constraint problem. You have some you have some density matrix with some eigenvalues, and you have the sum to one, and you're trying to extremize it, or maximize it in this case. Okay. All right. Now let me give you. So we want this entropy as a function of time. We developed all of this machinery to do that. But before I use the machinery, let me give you a quick argument for what the answer should be. From this free field theory intuition, we said that it's that what happens roughly is that you have these modes that escape. Let's say we focus on the right-moving guys. The modes that escape that are entangled with their partners behind the horizon. And this process just keeps happening. Remember, the black hole is stable, in that there's also radiation coming in. And it also happens on the other side. Okay? As a function of time, you just keep collecting more and more of these Hawking modes. And so you expect that the answer, S of B, the baths, should go as C, the number of species. Let's spell species. Times the rate of emission of these Hawking quanta, which is 1 over beta, times time. You expect an answer like this. And something that you should check is that the entropy is given by the following formula. Now, if we use this machinery, you get C over 3. Your question? No. C over 3 log, I'm going to ignore unimportant factors, cosh of 2 pi u over beta. At late times, this thing goes as C times 1 over beta times u. Okay?
So I forgot what u was.
Oh, u was time. Sorry. Yes?
For the metric was u independent, then the state.
So it again?
The metric is u independent.
Correct.
And the state is a vacuum inside. So why do we have an answer independently?
Yeah, good. The state, remember, so there was a time invariance of the state. That time invariance is not this time evolution. The time invariance is the boost time evolution. So this is a killing symmetry of this space-time. However, this time evolution is actually not a symmetry of the space-time. And so it's not a surprise that we got something that depends on going from this slice to this slice. These are, if you do this, it will be independent of you. Exactly. Okay, so now, what do we find?
One is H right generated by H right plus.
Correct.
H left, the other by H left.
Yes. So one is H right plus H left. The other one is H right minus H left. To be maximally confusing, this is the one that goes up on both sides. Okay. All right. And
sorry, I have a question.
Yes.
Could you just draw, say, 2 time slices which shows the time evolution of the full slice? Any one time slice.
So here's a full slice.
Right.
Then I evolved it to this. Okay. So here is okay. Let's plot various entropies as a function of time. One of those entropies is the total thermal entropy, S thermal. Here, this might be a little bit confusing, but sorry, no. Well, it's a constant. It's S thermal of the wormhole. That's what this W stands for, which actually is 2 times S thermal that we saw before. Okay, because the wormhole has. Okay. 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 Now, if you compute, but the answer that we got before, sorry, the answer for the von Neumann entropy just increases for all time. Okay. So this is S of the radiation. Okay. Now let's try to make sense of this answer. Okay, there are 3 scenarios. There are 3 ways of interpreting this answer. or at least 3 ways. The first way is to say that this thermal entropy is just nothing. It's just the number that we computed, and it has nothing to do with anything physical. And that where is it? That the radiation, the entropy of the radiation grows as time. And in order to save quantum mechanics, you would say that the entropy of the complement of the radiation, which is the wormhole, also grows with time. So this is one scenario. Okay? This scenario is bad because it would say that you can have an object inside ADS2 spacetime, which has finite mass. It can have an arbitrarily large amount of entropy. So this means that you can have as many states as you want at a given mass. I could have done this for as small mass as I wanted, at least in this particular example. You can have in the evaporating black hole case, you can start with a humongous black hole and let it evaporate. And then in this scenario, you would say that its von Neumann entropy, well, can be as large as the entropy of the radiation. But you can also feed it more matter and make it even bigger and let it evaporate down again. And so you can make its entropy at arbitrarily small mass as large as you want. This is kind of crazy. It says that you can have an infinite number of states below any energy. And so you would usually, some people have argued that if such things exist, you should have seen them in LHC. They would pollute scattering of standard elementary particles. This is the remnant problem or the bag of gold problem. Okay, so that's one scenario. The other scenario,
assume that beta is constant in time.
I built up my setup so that beta is constant in time. It's an eternal black hole. I've initiated all the matter coming in from infinity in such a way that it stays at beta. The other scenario is to say, okay, what about this? That the wormhole does something like this. But we don't know what the computation is. That maybe some magic comes in and it turns around the entropy of the wormhole. But if this is the case, then you've broken quantum mechanics, because you don't have the condition that S has to be equal to S rad. Oh no, sorry. You've broken quantum mechanics because while here you have a pure state of the combination of the wormhole and the radiation, here you don't have a pure state of the combination of the wormhole and the radiation. Because if it was a pure state, then the entropys must be the same. So in this scenario, you've evolved from a pure state to a mixed state. Something which is disallowed or cannot be achieved via unitary time evolution in quantum mechanics. Okay, and finally, there is the unitarity approach, which is to say, okay, some magic comes in and gives us this, but there's also some other magic that comes and fixes that and brings down the radiation entropy to also be the same. This is what one needs in order to save quantum mechanics. And I have 4 minutes. Right? Good. Okay. In 4 minutes, let me talk about the firewall paradox. Okay. Okay. So it's going to be very quick. How do we bring the entropy back down? The only way you can bring the entropy back down is to say that these modes, at some point in time, must not be entangled with one another. So there's no entanglement between these modes. But remember that the entanglement between these modes was implied by the fact that we have the vacuum in the W coordinates. So this implied that. But if you now require that this is broken, and this is then the state in the W frame is not the vacuum. And you can translate that to mean that an infalling observer would see some sort of excitation somewhere near the horizon of the black hole. That's the firewall effect. The firewall, the reason why it's called a paradox is okay. Let me just say that. So no, I'm not going to list all the postulates and so on and so forth. But anyways, that's the firewall that you might think has to be there in order to bring down the entropy.
What?
Yes?
Why necessarily there?
Well, somewhere. I don't know where it's going to happen. Or actually, sorry, ask your question again.
Why it has to be, I mean, if you're considering that region outside, completely outside.
The region completely outside. The region being...
Then you wouldn't have this. It's because you're this region calculating entropy across the front.
No, the region that I'm computing the entropy of is always outside here.
You don't want to kill Hawking's calculation completely. Very close to the right.
I'm computing the entropy of the radiation that escapes from space-time. And then from that, I'm deducing something about what has to happen inside.
So why necessarily on the horizon?
Because it's these modes that get captured here. This picture is a bit too. It's not doing distances any justice. These modes, when you come back, are actually extremely close to the horizon. So that's where they come from. So this point is actually like a, I don't know, well, it's a null distance now. And you might ask, well, good. Okay, I'll end with the following dramatic point. So here, it seems like at some point, you should start breaking entanglement. Okay, let's say that point is here. But there's a time symmetry in this problem. If it's here, I can boost the system to mean that it's anywhere on this horizon. We were doing this to the future, and well, there's nothing special about this side and this side, so it's also all the way here. But the same puzzle also holds going backwards in time. So that means there's a firewall here and here. So it would seem to suggest that this new effect that would bend down the entropy would create an excitation that, well, an obstacle for jumping into the future of the wormhole or in the past, or said differently, that there's just no interior in the future or in the past.
Why is it the paradox?
Yeah, but the paradox is not. The paradox is it's the hope. It's whether you can find a consistent description that where Hawking's calculation from the outside makes sense.
It does.
Okay. And that an infalling observer sees nothing out of the ordinary.
Maybe it does.
Maybe, but I'm telling you what the firewall paradox setup is. It says you have these two postulates. Well, they have more postulates. You have these two statements that an infalling observer sees nothing else.
Sounds like the cosmological constant paradox of Einstein. Maybe the universe expands.
Maybe. So then the next step would be to find the effect that generates the wormhole, the firewall. But what I'm going to talk about next time, I guess, is the effect that actually bends down the entropy. That this is actually the right scenario. And let me end with just writing down that this curve for the entropy, the one that follows what you expect from unitarity, is the famous page curve. And let me end with that. Thank you.
So what did you say was the right scenario? There's a file?
No. No. The right scenario is this for the entropy, but without the firewall.